Implementing Dijkstra's shortest path algorithm. Dijkstra's algorithm is a cornerstone of graph theory and computer science, providing an efficient solution for finding the shortest path between nodes in a graph. This article delves into the intricacies of implementing Dijkstra's shortest path algorithm, offering a clear understanding for learners and highlighting its real-world applications. What is Dijkstra's algorithm? Dijkstra's algorithm, named after computer scientist Edgar W. Dijkstra, is a greedy algorithm used to solve the single-source shortest path problem for a graph with non-negative edge weights. In simpler terms, given a starting node in a graph, the algorithm finds the shortest path from that node to all other nodes in the graph. It's a fundamental algorithm used in various applications, from network routing to GPS navigation. Key concepts. Graph, a data structure consisting of nodes connected by edges. Nodes represent entities in the graph. Edges represent the connections between nodes, often with associated weights. Weight, a numerical value assigned to an edge, representing the cost of traversing that edge. Dijkstra's algorithm requires non-negative weights. Shortest path, the path between two nodes with the minimum total weight. How Dijkstra's algorithm works, a step-by-step explanation. The algorithm operates iteratively, maintaining a set of visited nodes and a set of unvisited nodes. It assigns a tentative distance value to each node, 0 for the starting node and infinity for all other nodes. The algorithm then proceeds as follows. Initialization. Assign a distance value of 0 to the starting node and infinity to all other nodes. Mark all nodes as unvisited. Set the starting node as the current node. Iteration. For the current node, consider all its unvisited neighbors and calculate their tentative distances through the current node. Compare the newly calculated tentative distance to the current assigned value and assign the smaller one. After considering all unvisited neighbors of the current node, mark the current node as visited. A visited node will not be checked again. Select the unvisited node with the smallest tentative distance and set it as the new current node. Termination. Repeat step 2 until all nodes have been visited, or the destination node has been visited. Illustrative example. Imagine a map with cities connected by roads with distances. If you want to find the shortest route from your starting city to all other cities, Dijkstra's algorithm will systematically explore the map, updating the shortest known distance to each city until it finds the optimal routes. Implementing Dijkstra's shortest path algorithm, code example. Below is a Python implementation of Dijkstra's algorithm using a dictionary to represent the graph and a priority queue for efficient node selection. So, the Dijkstra function takes the graph and the starting node as input. Distances dictionary stores the shortest distance from the start node to each node. Initialized to infinity for all nodes except the start node. Priority queue is a main heap that stores nodes to visit, prioritized by their distance from the start node. The while loop continues as long as there are nodes in the priority queue. Yap.eapop retrieves the node with the smallest distance from the priority queue. The inner for loop iterates through the neighbors of the current node, calculating the distance to each neighbor through the current node. If the calculated distance is shorter than the current shortest distance to the neighbor, the distances dictionary is updated, and the neighbor is added to the priority queue. The function returns the distances dictionary, which contains the shortest distances from the start node to all other nodes in the graph. Real-world applications of implementing Dijkstra's shortest path algorithm. Dijkstra's algorithm finds applications in a wide range of fields. Navigation systems, GPS devices use Dijkstra's algorithm to calculate the shortest routes between locations, considering factors like distance, traffic, and road closures. 1. Network routing. In computer networks, Dijkstra's algorithm is used to find the most efficient paths for data packets to travel between routers. 2. Airline route planning. Airlines use algorithms similar to Dijkstra's to optimize flight routes, minimizing fuel consumption and travel time. Social networking. Finding connections between users in a social network can be modeled as a shortest path problem, where nodes represent users and edges represent connections. Robotics. Path planning for robots often involves finding the shortest path between a starting point and a destination, avoiding obstacles. 3. Logistics and supply chain management, optimizing delivery routes and warehouse locations to minimize transportation costs. Advantages and disadvantages. Advantages. Guaranteed to find the shortest path when edge weights are non-negative. Dijkstra's algorithm guarantees finding the shortest path from the source node to all other reachable nodes. Relatively efficient. With a priority queue implementation, the time complexity is O, where E is the number of edges and V is the number of vertices. Disadvantages. Does not work with negative edge weights. Dijkstra's algorithm assumes non-negative edge weights. If negative weights are present, it may produce incorrect results. For graphs with negative edge weights, the Bellman-Ford algorithm should be used. Can be computationally expensive for large graphs. While relatively efficient, the algorithm's performance can degrade for very large graphs. Blind search. Dijkstra's algorithm explores in all directions, which can be inefficient if the destination is known. A search algorithm, which is an extension of Dijkstra's, uses heuristics to guide the search and can be more efficient in such cases. In conclusion, implementing Dijkstra's shortest path algorithm is a fundamental skill for computer scientists and software engineers. Its applications are widespread, impacting various aspects of our daily lives, from navigation to network communication. By understanding the algorithm's principles and implementation details, learners can gain valuable insights into graph theory and its practical applications. While it has limitations, particularly with negative edge weights, its efficiency and guaranteed accuracy for non-negative weights make it a powerful tool for solving a wide range of optimization problems. Footnotes. Bast, H., Funk, S., Matijevic, D., Sanders, P., and Schultz, D. Route Planning and Transportation Networks. Algorithm Engineering, 17-59. Kouros, J.F., and Russ, K.W. Computer Networking, a Top-Down Approach. Pearson Education. La Valley, S.M. Planning Algorithms. Cambridge University Press.